Hello, Ken.
Hello. Sorry I'm late. I apologize.
Yeah, that's okay. Yeah. Okay. Let's see. How's the homework going?
It's going really good. The only thing that I was having trouble with was the kinetic energy of the relativistic particle. Um, just trying to look at some literature to figure out how other people have like handled that, I guess. So
We will also be doing that later in the semester in a more rigorous manner. Currently, you just need that equations, but do that more rigorously later.
yeah, from what I've seen, they changed the dt into like a d tau relativistically. Yeah, so that's kind of the method I was following.
But you don't need that detail in the homework, actually. You can manage just by pretending that this is a differential equation and just doing it, trying to get the Lagrangian. So it's easier than getting the tau and other things. But yeah, explore it. It's going to be a learning experience. So do it your way. Okay. We have a few homeworks. That's it. I think probably I mentioned this last time, but here, the homework 8 was it is due today. So that's March 30th, but on D2L, it shows up as April 1st. In fact, even after that, there is a lenience of you can submit it in the next 24 hours and all. So it's a lenience a lot of time. Okay, so homework 9. This is due on April 1st. It is a Thursday. Again, there's if you want more time, just let me know, and that's perfectly fine. And homework 10. So this is on Hamiltonian. This is yes, please.
If you're writing, I can't see.
Oh, I'm on the wrong board, I guess. Oh, there you go.
Thank you so much.
So homework 8 is on Hamiltonian. Homework 9, which we will be covering only today. So this is conservative principles, right? Conservation principles, like conservation of energy, conservation of momentum, and so on. Hopefully, I should be able to finish that. That's where that it's useful for me also to keep this flexible, in the sense that if I'm not able to finish it, then it can be postponed in that sense. Homework 10 is going to act like a midterm. So this is April 8th. So this is the new part. This will act as a midterm. And it also involves looking into, so it will not be covered in cloth, will not be covered in cloth, but there is a recording, associated recording out there, so you just have to watch that. So it's like attending a class for about 1 hour. It's my own video, so it is from last year, so you just attend to that. So recording should help. Or else just look up any resource. It doesn't have to be that you have to look into the recording. But notations wise, and what I mean is it often helps to have the same person tell you. But content wise, it should not be a problem. Okay. Okay, so we have been talking about change in the action due to all sorts of variations, basically the variation, including the variations at the boundary. So let's point this out. So let's say, let me say, today we are going to talk about symmetry. So we're going to use what we did last time, symmetry and conservation principle. Like that's what we wanted to talk about. Broadly, this is called Noether's theorem. It's pronounced as not the way I'm pronouncing it. I pronounce it pretty much like it's Noether's term. It is NU, I think, or it's closest to NU. It's hard for me to pronounce it. So look at, I think that itself is a good thing to look up. It's good to pronounce it the right way. Okay. So what do we mean by here? So let's go back. We have said that there exists an act. First, we define an action in terms of a Lagrangian. It is a functional. It depends on the position. Right? So let's say this is R. It is a function of time, implicit function of time, and it also depends on the endpoints. The system goes from T1 to T2. So it depends on R of T1 and T2. And you can say this is defined as T1 to T2, Dt. The Lagrangian depends on the position as a function of time. Velocity is dr by dt, which is also a function of time, and the time itself. That could be an explicit dependence in time. We showed that if you were to make variations on the left-hand side where there are R, T1, and T2, right? That's only 3 quantities you can vary. So if you say you make a variation in the path, so when I say what is am I doing, so R of T goes to R of T plus. So it's an infinitesimal variation in the sense that I make a small change in this path. This is a curve as a function of time in 3-dimensional space. This is a list of points, a continuous list of points, and that describes a path, and you're making a small change in that. And this is like saying that this is a function of time. So that's what we are, and that's arbitrary. But we also say that at T1, we can make T1 itself can change. So this is, oh sorry, this is delta R, right? I said it wrong. It's delta R. R gets displaced by this small change. Delta R. T1 goes from T1 plus delta T1. And T2 goes from T2 to T2 plus delta T. That's the complete variations, and we showed that under these variations, our action, the total change in the action can be put together in three different form or three different kinds of changes happen in here. The first one is T1 to T2 dt. I should also point out that when we did this last time, we did this for one-dimensional case, and that pretty much generalized it. It pretty much goes through in exactly the same manner. So that's dt, and we had delta r, and last time I think we used x, I think. So, but I thought I would use r. It's exactly the same. You have this Euler-Lagrange equations of motion showing up here. So this is dl by dr, which is a gradient with respect to the Lagrangian, gradient of the Lagrangian, and minus d by dt of partial derivative of the Lagrangian with respect to the velocity. I'm using the terminology that this is nothing but the velocity. That's just a notation. It's just to save space. There is nothing special in velocity. It's always derivative of position. But momentum is different. Momentum becomes a special variable. Unlike velocity is a notation, but momentum actually becomes an independent variable when you're talking about the Hamiltonian. That's your first variation. And the second piece is due to the change in time. And these changes in time, the way we did it, we made a substitution, and it partially goes in the global sense that it completely goes from one point to the other point, and partially it contributes only at the boundary. So we want both in there. So these are the new variations that's coming in. One is completely in the bulk, right? You can say in the bulk of the time. At every instant there is a change in a sense, and that's given as the L by dt plus was it plus or minus? Let's see. Yeah, plus, because when I set it to equal, then becomes a minus. As total derivative with respect to time, and I have dr by dt dotted with dl by dv. Seems like they're all coming up randomly, but it's all actually comes up all together, because once we identify these things, it's kind of nice. Right, that was one piece, and this is the interesting part, that is a piece that shows up only at the boundary. And remember the definition of potential energy in mechanics, introductory physics, that potential energy by definition is a function which survives only on the boundary, right? There is if you're going from one point to the other point, it depends only on the initial and final point. So that's the nice part of this term, that seems to be a function which knows only about the boundary, and that has a lot of information in that sense, and we'll see what we can conclude about that. And this is equal to, let me write this explicitly at this point. This is P, which is dl dv dotted with delta r. This time contribution comes only from the boundary, because this is a total derivative, so it survives only on the boundary. And minus of delta t times times the same expression of that. And again, I repeat that this third term, because it's a total derivative, contributes only at the endpoints T1 and T2. At this point, we say that, okay, these two are dynamical, position and time are dynamical. So any change in the action due to the change in position and change in time in the bulk is going to be zero. That's the stationary action principle, which means that these two have to be zero. Okay, so we invoke stationary action principle in the bulk, but that doesn't mean that this has to be equal to zero. This is not zero because this is coming only at the boundary. So it's a stationary action principle. Tells us that the change in the action with respect to the change in position in the bulk, right? So this is in the bulk. By bulk, I mean it's not on the boundary. That's equal to zero. So that implies that L by dr is equal to d by dt of L by dv. Right? So that's first statement. Again, stationary action principle, we say that the change in action with respect to time in the bulk, again, this is in the bulk, is equal to zero. Like at every instant of time as a whole path. And that implies that the L by dt is equal, or minus dL by dt is equal to d by dt of this whole quantity, that which is primarily the primal term. Minus L. Okay. So what is the variation? So stationary action principle imposes two of this to be zero, but there is still something remaining. So this leaves the variation in the action to be, there's still something remaining, and that's a third part. And that is delta W, the change in action, which gets contribution only from the boundary. So I can say this is equal to change in T2 minus change in T1. Correct. And that's equal to where G of T2 minus T1, where G of T is equal to this piece, right? dL by dV dotted with delta R and minus of dR by dt dotted with dL by dV minus of L times delta T. Is that very clear?
Yes, that's very clear.
Okay. So at this point, so this is just a summary of whatever we did last time. At this point, I also recall that if we use the definitions, which is useful, or write this in terms of Hamiltonian, we have the canonical momentum to be L by dV, and the Hamiltonian, remember, which is only a function of h and p, position and momentum, is defined to be the velocity dotted with p, the canonical momentum, v dotted with p, minus of L. Then I have my variation at the boundary to be the g function is written as p dotted with delta r and minus of the Hamiltonian multiplied by the variation in time at the boundary again, but each time could be the boundary, so that's the function of the time. Okay. Let me now write the action. So action is basically the Lagrangian. So let me go back and write it in terms of the Hamiltonian. So that's perfectly fine. Right? So let's so there are two quantities at this point. So let me concentrate on that. Let me say the action is now maybe write this in two steps. This is R, T1, T2. This has been defined as T1 to T2, Dt, L, or R, which is a function of time, velocity, which is a function of time, and T. Right? But remember, velocity is defined in terms of the position. It's not an independent variable. One can also show, I haven't shown this explicitly here, that if you were to start with a different action, which is not very surprising. So instead of having R position alone as an independent variable, define your momentum also to be an independent variable, actually the canonical momentum, and define your action to be this T1 to T2, T, and we have T dotted with V minus L, which is basically the Hamiltonian. That's also a valid action, and you will get the equations of motions completely. One can actually do this whole variational problem, including the boundary, and everything goes through, and you get the same thing at the end, like perfectly same thing. And we will find it convenient to use this. So we will write this as, like, instead of writing this as P dot V, we will actually write this as T1 to T2 dt. This is the Hamiltonian. Right? So this is R, which is a function of time, implicit function of time, momentum, an independent variable, an implicit function of time, and T. And if I were to make the change in this, the idea is that the change in the action after using the equations of motions contributes only at the boundary. So this is this gets only, so only getting contribution only at the boundary. I say is written as this total derivative here, and now this will be T dotted with delta with variation in R minus the Hamiltonian itself multiplied by delta T. This remains exactly the same. Okay. So let's see how do we make connection with what we said earlier, that symmetry we can learn something from symmetry. Okay, so let's do the simplest scenario, a reasonably simple transformation. So notice that we are making variations, correct? Again, I should say that we make some variations and ask what is the change in the action. And now let's, as of now, or at least maybe I should clarify this. When we used stationary action principle, we made a arbitrary variation. We didn't specify what kind of variation this is. There are special kind of variations you can make, but we said it is random, complete. Any variation you give me, it qualifies to be, or it qualifies when you are discussing the stationary action principle. Now let's specify our variation very localized, right? We are saying a special kind of variation, and that could be like you start from a position and you move the position. So this is r prime is equal to r, or let's say plus, let me put it as minus, plus or minus when deciding. Okay, minus, right? Minus of delta. First, let me just say I move it by a constant vector A. What that means is that a position of every coordinate in space is moved to the left by a point A. Basically, if you actively look at it as a coordinate transformation, the coordinates are moving or the observer is moving. Either could be an interpretation. We will be interested in infinitesimal variations. So instead of saying this is a finite change, we will make it a small infinitesimal change. So this will be called a translation. So infinitesimal translation. And let us ask, what is the change in the action because of this? But that's not completely sufficient to specify, because there is this momentum also, right? And let us go back and see, how does the momentum change? We do know in our, using our insight, we know that momentum is derivative of position, right? At least in the simplest scenario, it is a derivative. And if I take the time derivative of this translation, if it is fixed, there is no time dependence in this, that will be 0. So let me define, since I am defining my transformation, let me say momentum does not change under translation. So that's P prime stays the same. That's my definition of infinitesimal transformation. And P prime stays the same. Time also changes, doesn't change. So that's my definition of infinitesimal translation. Let me ask, how does the Hamiltonian change? So I have my action, which is equal to the T1 to T2 dt Hamiltonian, which is a function of R, P, and T. So if I'm interested in the change in the action, whatever is the change in my Hamiltonian, it will contribute to that change in the action. So this is just a constant variation. So I know that this will be equal to change in my action. Okay. This is partial, right? So this is not. So since this is not a function of time, this is just partial derivative. So that's a vector, and that's simply equal to dt or R, right? So is that clear how that comes about? Maybe I can elaborate on that. Notice H of R prime, E prime, is equal to H of R plus delta epsilon, comma P, right? Because P prime is the same as P. Then Taylor expand this. This is equal to H of R, comma P plus delta epsilon dotted with H over delta R. Plus higher order terms, but I don't keep them. So my change in the Hamiltonian is equal to delta epsilon dotted with H by dr, which means that partial derivative of H with respect to delta epsilon is equal to partial derivative of H with respect to R. Is that clear? Right, that's what I used in writing the statement. So that's one way of looking at this. So given the action, since action is written in terms of the Hamiltonian, the change in action due to this translation is given by the integral of the change in the action with respect to R. And change in action with change in energy with respect to what's known as energy, right? So this is the total energy if you want. But that's going to the physics part, but we are here trying to get a connection between symmetry. So this is now a symmetry, right? We are saying that, or if you change this, Hamilton changes. If the Hamiltonian doesn't change, that becomes a symmetry. Okay, so symmetry would be, so let's say what is a symmetry? Will be if this is equal to 0, you say that we have the action is, this implies that action has translational symmetry. But it's better than that in the sense this is given in terms of delta epsilon. When does that become? The Hamiltonian has to be independent of R, right? That's actually a much stronger statement. Is delta H over delta R is equal to 0. That implies H is independent of R. If the Hamiltonian is independent of position, then apparently this, then we say that our system is independent of translation. Like we are saying, for example, mgh, right? When we say Hamiltonian, remember, has connection with energy. So if the energy is mg times h, that means it depends on the position where you're standing relative to the Earth. So that means you don't have translation symmetry. If you go up, it's not the same as going down. So you don't have translation symmetry. But it is independent of the position x, horizontal distance, which means that there is a symmetry. If you go horizontally, it doesn't know that you have moved. The system will not understand at all. If energy is the only parameter you're looking at, it will never know that you've actually moved. So in that sense, it's a translation symmetry. Clear? Okay, so, but we have more information here, right? This is all using the standard simple action, but now we have some more information about the boundary. So let's go to the boundary and ask the same question. So let's analyze this by looking at the boundary. We also know that the change in action, right, is also given in terms of a boundary at the boundary. So this is T1 to T2 and P dotted with delta R minus H times delta T. Right? That's our expression for the variation in the action. Again, the same variation in the action, but now it is given in terms of quantities at the boundary. Correct? Let me use this fact that we learned. Delta R for us now for translation is delta epsilon, and delta T is equal to 0. Agreed? That's our definition of translation. And the translation we have talked about, so there are two ways of defining translation, remember. The translation could be that you move things differently at each position or at each time, for example. The translation could be time dependent too, but we are saying it's a rigid translation, right? We are not making this quantity dependent on time, which means that I can bring it out, right? So this means that this can come out of the time derivative, out of the time integral, and this is the same as delta epsilon dotted with T1 to T2 dt dp by dt. Is that clear? Only for a rigid rotation, sorry, rigid translation. So if delta epsilon is independent of time, in fact, we say that this is a rigid translation. So this is called a rigid translation. That means every point is translated by the same amount, every point in space. Okay. Now what do we learn? I take this to the left, and I learn that the change in action with respect to epsilon is equal to T1 to T2 dt dp by dt. Which is, since it is at the boundary, this means that this is nothing but P of T2 minus P of T1. So this is an independent scenario. So this is, let's say 1, right? So this is 2. Earlier, we have already said that change in action due to the rigid translation is also equal to T1 to T2 dt change in the Hamiltonian with respect to position, right? That's another statement, independent statement. Correct? Is the logic clear as of now? This is all algebra, but now I'm going to connect these things. These are independent two statements.
Yeah, that's very clear. I do have one question in the
Yes.
exact opposite of like rigid translation. So regular translation is dependent on time.
You can depend. For example, if you define R to be equal, R prime to be equal to R plus a small epsilon, which is position dependent and time dependent. That's a complicated translation, right? But what we are saying is that no, that's not what we're saying. We are saying no position dependence, no time dependence. At every point, I move it by 1 centimeter. The whole universe is rigidly moved by 1 centimeter. That's different by you squeeze, and you can squeeze at each point a small translation, but On the left corner of the universe, you make it by 1 meter. On the right corner, you make it by 2 meters. That's also a translation, but this is a rigid translation. The
Okay,
other
thank
one,
you.
the other one is much more complicated and much more richer if you want, much more work to deal with it. Okay. Now, if with this information, now notice what you're saying. If, so let's start with if the system, by system I mean if the system, that means the Hamiltonian, or the Lagrangian. If the system has translational symmetry, or rigid translational symmetry, rigid translational symmetry, right? Then you have the H by the R is equal to 0. Agreed? That's what we defined earlier. Okay? That means, now you're going to notice the implication. So that's down here. This has gone to 0 now. This quantity has gone to 0. That means the change in action is 0. That implies that the change in the action with respect to change in, so this is actually not really a complete variation, functional variation. It is just a change in the action with respect to rigid rotation. That's equal to 0. It doesn't matter how I write it. Okay? So if this is 0, that's 0. If that's 0, the left-hand side of the second equation becomes 0. Which means this is 0, right? Which means these two are equal. This implies that P at any time is equal to P at any other time. Okay? Which means that, let me write that as dP by dt is equal to 0, right? Or P is conserved. Right? So if the Hamiltonian is translationally symmetric, your linear momentum has to be conserved. Very broad statement, no system involved. Like it is any system, give me any system. If the Hamilton or Hamiltonian is independent of position actually, right? Of that particular variable, if it is independent of position, the momentum associated with that will be conserved. Okay? No work needed, just immediately you conclude that. That's the connection between symmetry and a conserved quantity. And you can go the other way. I can start from if the momentum is conserved, then this is equal to 0, and that's equal to 0, then the system has to be symmetric too. So this is what is called the connection between a symmetry and a conservation principle. Usually, whenever a system is symmetric under some transformation, there is an associated conserved quantity.
And here that conserved quantity is momentum, right? So,
in this case, the conserved quantity is the linear momentum. Is that the question? Is that what you said?
yeah. And it can be extended to other conservational forces, I guess.
Exactly. So I'm going to do next, I'm going to do Hamilton. In your homework, there are 3 things you do. One is the momentum, which I did here, Hamilton energy conservation, And the third is angular momentum conservation. These are the basic ones, but it can be extended to various things. There's a whole rich, that's what Noether's theorem is, that you can extend this to any symmetry you want. It's a matter of how cleverly you can see that symmetry and how you can do that transformation. Okay, clear? Okay, so now let's do the same thing for time translation. Let me erase this. Or rigid time translation, right? Okay. I had to define my time translation. So I say t prime is going to be equal to t minus of, I'll make it an infinitesimal translation, and it is rigid in the sense it is a constant with respect to position and time, right? So there is no position dependence, no time dependence, right? So there is no position dependence, no time dependence, correct? So it could have been a position dependent and time dependent quantity. By rigid, I mean there is no position dependence, no time dependence. But notice that in the Hamiltonian formalism, we need to provide how does the position change under the same translation? And I say that position doesn't change. Under a time translation, position doesn't change. And how does the momentum change? Remember, momentum seems like there is a derivative with velocity, right? So one has to be careful. But remember that if you say t prime is equal to t minus delta s, dt prime is equal to dt, right? Change in times doesn't change. So momentum involves a derivative, so that's a change in time. So any change in time does not care for the translation. So momentum remains the same, even though one would have thought that momentum in the intuitive way, it is derivative with respect to time. So if you change time, momentum should change. No, under rigid translation, momentum does not change. At least that's how we are going to define this. So this is going to be our rigid time translation. Okay. First, let's ask, how does the Hamiltonian change, right? Or how does the action change? So the change in action is given in terms of, so this will be T1 to T2, Tt, right? And the Hamiltonian can change, so this is change in action will be h of r prime, comma p prime, comma t prime, minus of h of r prime or r, comma p, comma t. So that's our change in the action in the explicit way, right? If I don't worry about the boundary and all that. That's equal to, so that's the same as t minus, so that's a Taylor trans, if I do the Taylor expansion, I get d1 to d2 dt, and since t prime is a delta s, so I have a minus delta s times dh by dt. Notice that's a partial derivative with time. So I learned that the change in the action, and since it's a rigid translation, I don't have to write it as a functional. So I say this is the change in action with respect to this rigid translation parameter S is equal to minus of T1, T2, dt, partial derivative of H with respect to T. That's my first relation. But I could do the same thing from my boundary variation, and there it is, the change in the action is equal to T1, T2, dt, and T times dotted with delta R minus H dotted with, oh sorry, this is total derivative, right? H times delta T. For rigid translation, this is equal to 0. Change in R is 0. And time is delta S. Actually, T prime, so this will be minus delta S. It doesn't matter whether it defined, that's a matter of definition, how you define your translation. And again, we get, if that is the case, this is equal to T1 to T2 dt, d by dt of H delta S. It can come out of the integral. Notice this is a constant, so that is the same as delta S T1 to T2 dt, total derivative of H with respect to time. And we conclude that partial derivative of the action with respect to the rigid translation parameter S is equal to dH by dt. Okay. Now we have to ask, what does it mean to say the Hamiltonian is independent? What do we mean by the Hamiltonian is symmetric under translation? We mean by this, right? This is what we mean, the partial derivative. So there are two possibilities. The total time derivative could be 0, or the partial derivative could be 0. In fact, it is going to be the same thing. It is not obvious at all that if this is 0, if the partial derivative with H is 0, the total derivative H should be 0. That's not obvious at all. Correct? But what we are going to say is that if it is symmetric, so let's make the symmetry under time translation implies that H is a constant in time. So H does not have explicit T dependence. Like different ways of saying the same thing, correct? Oops, can you read that a little bit? Is that readable? So if the Hamiltonian has no explicit time dependence, we will call that Hamiltonian to be symmetric under time translation. That means this is 0. If this is equal to 0, the change in action with respect to that parameter is 0. If the change in action with respect to that is 0, you come down, and it seems to suggest that the total time derivative of H is 0, and that's the statement of energy conservation. Right? H is a constant then. It seems like it is obvious here, oh, partial derivative means, but it's not. Partial derivative of something equal to 0 does not imply that the total derivative of the quantity is 0. In trivial systems it is, but in more complicated systems it's not obvious. at all. And this means the Hamiltonian is a constant, right? Hamiltonian is a constant or conservative, right? And that quantity is interpreted as energy. So Hamiltonian is interpreted as energy if this is conserved. Like even otherwise it's not, but then it's an open system. So, is that clear? It goes almost parallelly like earlier. Okay. Okay, next we want to do rotations. But rotations has a little baggage to carry in the sense that we have to introduce infinitesimal rotation, and let me spend the next 15 minutes or so filling that gap, but this is available everywhere. If I'm not able to finish it, you just look it up because it appears in your homework. Okay, so let me try to do this. Now, first of all, so we are going to say rigid rotations, right? Let me define what is rigid rotation. Are you available after the class for 10 minutes or so that I can extend this discussion a little so that we can finish? Okay, so what is rigid rotations? We are going to define the following way. So R prime, first of all, T prime, right? So T prime does not change. So T prime is the same as T itself. Time, rotation has nothing to do with time, right? That's obvious. Right? And what about position? Position changes under rotation, but we are talking about infinitesimal rotation. So we'll say this is delta R. Right? And this delta R is going to be of a special kind. It can be written as, let me write this, delta R is equal to a parameter which describes rotation, which involves angles here, delta omega, crossed with the position itself. That's what infinitesimal rotation is, right? So that's what I want to convince you, that this is actually what happens under an infinitesimal rotation. So I'm going to derive this formula for you in a few minutes. But once you have this, then you can do your homework. I won't, like the analysis that you have to do about conservation principle, that's your homework. Okay, that I'm not going to do. But what I'm going to do now is to derive this for you, why this is rotations. And I have to also define momentum, right? Momentum actually goes, transforms under rotation, and it transforms like very similar to rotations, right? Because any vector has to transform under rotations the same way. Okay. So this will be your definition of rigid rotation. And then you do the same analysis that I did, but it is slightly harder because these are vectors. You are having a mixed quantity, and so you have to do a little more work on it. It doesn't come out, but that's the details. But overall, the same idea goes through. Okay. But now let me say, why is so infinitesimal? This should be infinitesimal, right? So infinitesimal. Rigid rotation. Okay, what do I mean by that? First, let's define a standard rotation. Any rotation can be thought of as three rotations about three different axes: x-axis, y-axis, z-axis. If you want any arbitrary rotation, you can think of it as first you rotate it about x-axis, then you rotate it about y-axis, and then you rotate it about z-axis. Right? You can reach anywhere you want that way. Okay. So let's define our first rotation as x prime. So this is your R prime, by the way. The vector R prime. I'm going to write it as 3 components. Is that okay? So the vector R prime has 3 components, X prime, Y prime, or Z prime. And this has, this is, if I make only one rotation, that is about the X axis, then I will write this as, so since it is about the X axis doesn't change. Rotation, when you make a rotation about the X axis, the X components do not change. And the other components change by, let's say, let's say the angle is omega 1. Okay, that's a rotation which you should have seen it somewhere or the other, right? This is rotation about x-axis. Is that clear? Okay, familiar? Okay. But I'm not interested in, this is total rotation, right? I'm interested in a tiny infinitesimal rotation about the x-axis. And how do you get that? You make small angle approximation, right? Replace all the cosines with 1, all the sines with smallest angle. Right? And since this is under infinitesimal rotation, so this is approximately equal to, right? So this is approximately equal to 1, 0, 0, 1, 0, and this should be omega 1, but let me say this is delta omega 1. Since it's a small rotation, let me make that delta omega 1. Is that clear? Clear?
Yeah, that's very good.
Which can also be written as 1, 0, 0, 0, 1, 0, 0, 0, 1. That's the identity matrix. Plus a small change from the identity matrix, which is 0, 0, 0, 0, 0, delta omega 1, 0 minus delta omega 1, 0, acting on x, y, z. Okay, so my new vector x prime, y prime, z prime is equal to, when the identity matrix multiplies x, y, z, I get back x, y, z itself. And the change variation is nothing but, as a small, like I have to multiply that carefully. So this is, so this is x remains the same. Delta omega 1 multiplies z, right? So let me say that's x3. Right? Z is, I have written it as x3. Right? That's just to get some notation there. Minus delta omega 1 x2. Okay, y is x2. correct? Is that clear?
Yeah, that's clear.
Okay, so now this is only about one axis. Now I'm going to do 3 axes. Okay, so your general rotation, x prime, y prime, z prime, can be written as rotation about 3 axes, correct? So first I will do x, then I will do y, then I will do z. So this is the third z rotation, which is cosine of omega 3, right? Sine of omega 3 minus of sine of omega 3 cosine of omega 3 0 0 1 0 0. Then another rotation, this is cosine omega 2 0 sine omega 2 0 1 0 minus sine omega 2 0 cosine omega 2, and the one about the x-axis, which is 1 0 0. Okay. Notice the small change in the y direction. When you talk about the rotation in y, you put the negative sign in the wrong place, right? In the opposite diagonal element. That is so that there are some transformation properties with rotations under group transformation. Just to get that very neatly in an ordered way, you do the change here. Okay, that has to do with some group properties. But at this stage, you can take it as a notation, right? But there is a reason for that. You can change it here, but then some symmetry there will come up with a negative sign. Nothing wrong in it. It's just elegant to not to have it there and put it in here. Okay, that's just a choice. Make the infinite swell change. The moment you make this infinite swell, then you say x prime, y prime, z prime is equal to, you say this is 1. Right? This is, you make this delta omega 3 minus delta omega 3, 1, 0, 0, 1. So x1 is 1, 0, 0, 1. This is minus delta omega 2, 0, minus delta omega 2, 0, 1. The third one is 1, 0, 0. Okay. Again, I can split this into all the 1 plus 1 plus 1 plus, and I keep only the leading order. Okay, whenever two infinitesimal quantities multiply, I get rid of it. Right, that's the idea of small angle approximation. Right, keep only the first contribution, don't keep the second order contributions. If I do that, I get, so this this is going to be x, y, z plus so this is, yeah, maybe we need a quiz, right? So finish this step, okay? This is just algebra from this step to this step. It's simply going to be algebra. And this is going to be, let's say, minus here of of delta omega 2 x3 minus delta omega 3 x2. The second one will be delta omega 3 x1 minus delta omega 1 x3. So notice the pattern there, 2, 3, 3, 2, 3, 1, 1, 3. And this will be delta omega 1 x2 minus delta omega 2 x1. Okay. So this is quiz. Okay, yeah, finish this as a quiz. It should, and remember, drop all the higher order terms. Okay. But can you see any pattern here? Do you see any? What is this equal to? If these are the three components of a vector, what is that vector equal to? And that's sort of our result. So let's see how does that come about. Let's do I, J, K. Like think of cross product, and let us say these are the components of a vector. And take the determinant. Right? That's a cross product of two vectors, correct? The way I have written it. And if you were to evaluate the components, you will see that that's exactly this vector. Which means that, so it is sort of straightforward once you identify that. This is actually R prime. So under rotations, under infinitesimal rotations, how does your position change? Right? That changes as a cross product of delta omega crossed with position R. Okay, so that's your infinitesimal, rigid infinitesimal rotations. Okay, and you will need to use a little properties of vectors. Remember, the hint in your rigid symmetry principle is that whenever you have A dotted with B cross C, that's also equal to A cross B dotted with C. Right? So that helps. Like those use vector identities in that, and you should be able to get that. But if you have difficulties, feel free to ask questions, right? If you don't reach the answer. All this. Okay, that's all. Okay, thank you.
Okay, thank you.
Yeah, I can.
Bye.